Hello, you kooky and crazy kids. This is Mr. Williams here with a much shorter lecture this time, our second lecture for dynamics. Today we're going to be mixing things up, talking about variables and proportionality. So we're not really going to talk about dynamics per se, but this is an excellent time for us to switch gears a little bit and move towards working proportionally and variably versus working with more concrete values. So let's start with this bell ringer problem. I'd like you guys to pause this video and see if you can solve this problem all on your own. Then I'm going to walk through how it's done. So we have a bullet, begins at rest and accelerates down a barrel of a gun to a speed of 800 meters per second. Now, first I want to look at this kinematically. And I have, in terms of kinematics, that my initial velocity is 0. I have that it goes to a final velocity of 800 meters per second, and I know the length of the barrel, the length over which it accelerates is 0.2. So I can use my third kinematic equation here, end up doing 800 squared divided by 2 times 0.2, and we get a ridiculously large acceleration of about 1.6 million. 0.00000 meters per second squared. You might be thinking, oh my gosh, did I do something wrong? No, bullets accelerate very fast, very quick acceleration. And so that is the correct final value. Now find the force on this bullet. Well, force is just equal to mass times acceleration. We know the mass of the bullet is 0.4 kilograms. So we just multiply that times our acceleration. We find that we get a force of 64,000 newtons. And again, just using Newton's second law there, F net equals ma. Find the force on the gun. Well, remember Newton's third law. In this case, we have a gun that applies a huge force of 64,000 newtons to the bullet. And then what is the backwards force on this gun going to be? Try to undo, but I don't. Okay. What's this backwards force going to be? Well, it has to be equal and opposite. The gun, while applying a force to the bullet applies a force backwards. It kicks back. This is what we in the gun firing community, that's not me, but other people in the gun firing community call a recoil or a kickback. Some guns recoil heavier than others depending on the force applied and depending on the size of the bullets. So what is the force acting on the gun? It has to be the same, 50, 60, 400 newtons, but we could add the caveat that it is backwards compared to the forwards velocity of the bullet. Forwards, you could have aimed the gun in whatever direction, but whatever direction the bullet travels, the gun's going to kick back in the opposite direction. Now, could we find the acceleration of the gun? Absolutely. Again, just using Newton's second law here. I know the net force. I know the mass of the gun is 2 meters per second squared. Divide those two, and what's 6,400 divided by 2 would be 32,000 meters per second squared. A very high acceleration as well, but not quite in the realm of that the bullet was traveling. We wouldn't expect it to accelerate quite as fast with the difference in masses. Now lastly, find the range of the bullet after it leaves the barrel. Well, now we just turn this into a projectile motion problem. We were told that the height of this was 2 meters. I'm going to clear all of this to make some room here. So now this is really just a bullet is traveling at 2 meters per second. We are asking ourselves, how long is it going to take to fall this vertical distance of 2 meters? Using t-fall here, I'm going to find the time it takes to reach the ground. So 2 times 2 divided by 10 and take the square root of it. And that gives me a time of 0.63. Again, we could think about this in terms of kinematics or just using t-fall. You can use t-fall whenever we have no vertical velocity, which we do not in this case. We only have horizontal. And then if it takes that long to reach the ground, I wrote 2 meters per second here. It's very different than the 800 meters per second it should have. Every second, it moves 800 meters forwards. So we know it's not even going to get 800 meters. It's only going to get 505 meters forwards. And I just did 800 times 0.63 to find that. So this is a very mixed problem here. We had kinematics, we had projectile motion, and we had dynamics at play here. Get used to these kinds of questions where we're going to be asking you a lot of different aspects of the bullet, both kinematics and dynamics. You got to be able to apply them both. All right, so how long would an object take to travel a distance d at a constant rate of v? What's the mass of an object if it takes a net force F net to accelerate from rest to a speed of v over a time t? What are we seeing here is rather than giving you a number, I'm giving you variables. And let's first think about this in terms, what if I didn't give you variables, I give you numbers? What if I gave you a distance of 10 meters at a constant rate of 2 meters per second? Could we figure that out? Well, that just seems more manageable, right? If I just plug in different numbers in there. Because if we want to go 10 meters and it goes 2 meters every second, well, you could figure that time would end up just being delta x divided by v. And then that comes out to be 10 over 2, which comes out to be 5 seconds. But I don't want numbers. I want just variables. I want a distance d at a constant rate of v. All I need to do to solve this problem is understand, well, how would d and v be related? How is distance related to velocity? And a constant velocity at that. Well, velocity displacement is just equal to velocity times time if it's a constant velocity. And so I know rather than a displacement, I'm just going to say d equals v times t. And rather, now I just want to divide because I want this in terms of time. And now I know I could take any distance and any velocity and turn that into a time. This is a lot more useful to have an equation versus than just an answer of 5 seconds. That 5 was only good for the case of the 10 and the 2. But now I have an equation that can be used to solve for any case. And especially if we're doing an experiment where we're going to have a lot of D's and a lot of V's, then this is way more useful to have. Let's do the same thing for the second one. What's the mass of an object if it takes a net force of F net to accelerate from rest man, there's like a lot of spelling mistakes in this one, to a speed of v over a time t. Well, how are these things related? Well, I know F net is related to the mass by the acceleration. I'm not given the acceleration. I'm given that it goes from a speed from rest to a speed of v over t. Well, I know acceleration is delta time over t. Well, in this case, if we start from rest, that's just going to be v over t. So let's put this all together. V over t is really my A. So F net equals mass times v over t. And then flip it one more time. I don't want to know what F net is. I want to solve for mass. So if I rearrange this equation and solve this for mass, well, then I multiply both sides by t, and I divide both sides by v. I find that mass is equal to 4 F net times the time divided by the velocity. And that's going to be the mass of any object in this case, if it did in fact accelerate to whatever speed v over a time t, given the net force applied to it. Okay, and then lastly, it's the same kind of thing, but now I'm just showing you further that I could use whatever symbols I wanted. I just threw in an ampersand here, the and symbol, for a time of pound or hashtag. How far an at symbol measured in meters will it travel? Well, this, I think, it looks way more confusing, so let's replace this with our regular stuff. An object accelerates from rest at some acceleration for a time of t. How far would the displacement be will it travel? And I even know that it does start from rest. Well, I just need a kinematic equation here for how far is it going to travel. And I have that delta x equals vx naught t plus 1/2 a t squared. And I know that it initially starts at rest, so I can ignore that. So then I'm just going to keep moving upwards here. I know delta x is then equal to 1/2 a t squared. And that works for this problem. But now, in this case, I don't want delta x, a, and t. For whatever reason, I decided to use these crazy symbols. So I can say at symbol, our distance, is going to be equal to 1/2 times my ampersand. Oh, I can't draw an ampersand. That was literally my best. Sorry, guys. And then times my time, which is pound, and we just need to square that pound. So I can replace this exercise really just to show you, we can replace anything with any kind of symbols, but we use A and T and delta X and V because those, it's a lot easier to remember, okay, A means acceleration, T means time, rather than trying to remember, okay, pound symbol means time and my at symbol means displacement. A lot easier to just do it in terms of these variables and get an answer like this. All right, you guys are going to see this problem next in your notes. I'm actually going to skip this problem because I don't want to do this with an angle and off of a cliff at the same time. So we're going to skip past this one. We will see this later on, like using angles, but we're not going to do this problem specifically. So let's move forward to this one. An object of mass m, initially at rest when it has a force applied to it with a force of friction resisting its motion, determine an expression for the acceleration of an object. Well, as always with any kind of dynamics problems, free body diagrams can be useful. We have a mass of m, we have applied force backwards, we have friction acting on it. We could assume that we do in fact have gravity and normal force acting on it as well, but in these two cases, these are just going to cancel out. So if I want to determine an expression for the acceleration of the object, well, we know F net can tell us the acceleration of an object. And in this case, what would my net force be? How would I find it? If these were numbers, if I knew, I know the applied force and friction, I could throw in anything. Say the applied force was 10 and friction was 2. What would the net force be? I would just subtract those two forces. I would do F applied minus the force of friction. And then that's going to be equal to the mass times the acceleration. I want an expression for acceleration, really an equation, I shouldn't say expression here, for the acceleration. Well, that's going to then be F applied minus the force of friction divided by m. If you're wondering what that K stands for, it stands for kinetic because we have friction from the motion of an object. And we will see why we need to specify that in our fifth lecture when we talk about friction. If the object travels a displacement delta x, what's the final speed of the object? Well, it was initially at rest here, so v naught is 0. I know that we travel delta x, and I also know the acceleration. I know the acceleration is this nonsense, F applied minus Fk divided by m. What is the speed of an object? I'm looking to figure out what's that final speed here. Do I have an equation that relates these values to each other? V naught, delta x, a, and v. I absolutely do. I'll rewrite this over here. Oops, nope, I want to keep recording. I can use my kinematic equation, v squared equals v naught squared plus 2a delta x. And in this case, I just want to rearrange this equation for final speed. I actually already have that. And so that's going to be equal to, v is going to be equal to, this is at rest, so we can cancel that out, 2 times a times delta x, and we take the square root of that. Now, I want this in terms of the variables that were given, though. I'm not off the get-go given a. What I'm given is f applied, fk, and m. So all I have to do now is substitute in what is a. And so let's rewrite this over here. I'm going to get rid of this, and I'm going to remember it's a is f applied minus fk over m. And so all together, I would have a final expression. V is equal to the square root of 2 times f applied minus fk over m. And I multiply that times delta x, and that will tell me the final speed of an object. Now, what good does this do me? Again, like why did I take the time to variably get an answer here? Well, one, you're going to be requested to do this often, very, very often. So starting now, this kind of practice is going to be very beneficial for you down the road. You need to get used to working with variables and not working with numbers. But like 2, now you can choose any f applied, fk, and delta x and m and get an answer for the final velocity. I could pick 4 random values right here. If the mass was 200 kilograms, f applied was 900, fk was 500, and delta x was 60. Can we find the final speed of an object? Absolutely. We see all we have to do is plug those values into this equation here. This tells me how certain variables are related to other variables. And then if we have this expression, I don't have to restart at the beginning of solving, because I would have just solved for A, then I would have solved for V, and then I just have one number. But now I can plug in, now that I have it solved for V, I can plug in any values. I could change any of them. So I encourage you to test this, plug in those values, and see what that final velocity is going to be. All right, an object travels a distance of x after traveling constant speed for a time t. How much farther would it have traveled? How much farther would it travel after traveling for 2t if the speed remains constant? What about if you quadruple the speed? So now we're getting into the realm of proportionality. An object travels a distance x after traveling at a constant speed of a time t. How are these three variables related to each other? X and t. And we have a constant speed. Why don't we just call that v for logic's sake? Well, I know x is going to be related to the velocity and the time by just x is v times t if it is a constant speed. And we are asking, if I double the amount of time we travel for and I keep the speed the same, how much farther would it travel? Think about it this way. X equals v t, and I'm looking for, if I now have twice the amount of time that I travel that velocity for, how would x differ? When we set up a proportionality statement, which is what I did right here, I'm trying to make this equation balance. I have now doubled the amount of time. What effect would doubling the amount of time have on the distance? Well, you're going to go twice as far because you just traveled the same speed but for twice as long. You're going to go twice as far. What would happen if you would quadruple the speed? Well, we just change those 2's with 4's, and you can guess that we'd have now 4t, and now we'd have 4 times, whatever, blue's fine, 4 times the time. Now we're going to have 4 times the displacement. And this might seem a little unnecessary to do for such a simple problem, but what if we didn't have a simple equation? Now let's try that here. An object travels from x, from slowing down, from v to rest given a constant deceleration. If the deceleration remains the same, how much farther would the object travel if it slows from 2v to rest? How about 3v to rest? So what is an equation that would relate x, v, initial velocity, or sorry, final velocity, this is initial, rest is v naught, and actually v naught is equal to v, and this is our final velocity given a constant deceleration. I need my third kinematic equation here, that v squared equals v naught squared plus 2a delta x. It's slowing from a rate of, given a constant deceleration. So here we actually have 0 squared equals, our initial velocity is going to be positive. We're just going to call that v because that's our initial. And then 2 times, I'm actually going to go right ahead and make this negative for simplicity's sake, because what's going to happen here is we're actually going to subtract a v squared from both sides. So we're actually going to have a negative v squared equals a negative 2a delta x. And again, all I did was algebraically just manipulate that equation. And we see when I do that, though, that these negatives cancel each other out. And that's why it's important that we made the acceleration negative, because it is decelerating. And so just so our signs all work out here. So let's simplify that a little bit. If those negatives do really go away, we just have v squared equals 2a delta x. That's now, so again, this is why we need to be able to solve things variably. Now we want to know, if I start changing things, how is my displacement going to change? I'm going to keep my acceleration constant. It's going to be the same a, but what's going to differ is my initial speed. Now I want to make another proportionality statement. And we have to make sure that we do something like this is equal to 2a, going to remain the same, and then delta x. Now, one place people sometimes get confused is with this 2 right here. Well, this 2 was a part of the initial situation. That's just a constant value. Similarly, of how the a is just a constant value. We really don't even need to bring this along for the ride. What I'm saying is that this, how is my velocity proportional to the this delta x. And that symbol right there is alpha, and it means proportional to. And it allows me to drop anything that we're being constant, anything that we're remaining to be constant. But think about it before we jump into proportionality. Let's think in terms of the equation. What am I doing to v in my first case? Well, I'm doubling it. I'm going to have twice the amount of velocity that I did before, and I want to know how is that going to affect the acceleration. Well, when I double that v, in terms of the whole left-hand side of that equation, that 2 gets squared. And that's like me saying that I have 4 times the amount that I had before. This is going to simplify to 4v squared. And that's going to be equal to 2a, also is the same as before. And so we're asking, how is the delta x going to change? Because the 2 can't change and the a can't change. How much farther would we have gone? We would have gone 4 times as far. What would happen if we were to triple the initial speed? And so we can keep the same statement. Now just triple this. Well, then if we triple that, well, that'd be 9 times as much on the left-hand side. So we're going to need 9 times as much on the right-hand side. Since displacement is the only thing we're allowing to be bigger or smaller, because A has to be the same, then we're going to have 9 times. And again, don't get confused with this 2 here. The 2 is part of the initial expression. The 2 just comes in to relate the velocity and the acceleration. So we need to only focus on like what value are we adding to either side to come up with this. We can test this out if you want, and if you really do, I encourage you to test out. Start with like throw some values in there. Say an object travels 10. Say it has it's going at 10, an acceleration to -1, and we can solve this then for how far is it going to go if it goes to rest. Then make the acceleration 20. Make the initial speed 20. Keep the acceleration the same, and you will find, solving the equation the second time, that it will go 4 times as far. If we triple it, we change the initial velocity to 30, keeping the acceleration the same, we will find that it goes 9 times as far than it did in our initial case. All right, an object with a mass m accelerates to a rate of a given a force of F net. How would the acceleration change? We should drive 32 times the force and increase the mass by 8. This seems crazy, but it's actually really straightforward because our equation to start with is really straightforward. We have F net equals ma. We are changing a couple different things. Ma. We want to keep the same proportionality because we're asking how would the acceleration change if we have 32 times the force that we did before and increase the mass by 8. How would the acceleration change compared to how it was before? Meaning we just need to keep this proportional. So what value of A is going to make this whole statement proportional? Well, that's just going to be 32 divided by 8, which comes out to be 4. And this makes sense because then we'd have the 32 in red on both sides of our equation. 32 F net is going to be equal to 32 times mass times acceleration. And then we have things that are proportional. All right, I'll let you do this last one on your own. If you have any questions on it, please come and see me. If you have questions on any of the proportionality stuff, come and see me. Go ahead and start out with this proportionality worksheet because it is just doing all kinds of proportionality statements. Each one, we start with the correct equation. If we were running in this equation, what would be my correct equation to start with? Well, probably T fall, 2h over g. And then we want to just start changing some values. If I double the mass, how much longer is it going to take to fall? Trick, is there mass in here? No. Is the time it takes to fall related to the mass? No, we did a lab that proved just that. But if we change the height, that does, in fact, affect the fall time. And so hopefully you can correctly pull that. Sorry, this is a confusing way to write it. 2h. If we have 3 times the height, how is that going to affect the time that it takes to fall? Well, would it be 3 times the time that it takes to fall? No. It'd be the square root of 3 times it takes to fall. And if you're not really quite sure why that is, again, I encourage you to come and see me and do the same kind of work on the proportionality worksheet. You hit any snags or snafus,